So welcome everybody to the second series of webinars for the Flow-MER Friday. For those of you who haven't run into me before, I'm Ross Thompson. I'm a professor at University of Canberra, and I'm co-lead of the Flow-MER project, and you'll meet my other co-lead in just a second. So before we go any further, I do want to acknowledge the traditional owners of the land on which we meet today, realising that there are people from all over Australia who are with us today. So I want to express my respect to all of those traditional owners, and particularly to the traditional owners of the Murray-Darling Basin and of the selected areas which we primarily work. I'd like to recognise their ongoing connection to country and unique ability to care for country, and commit ourselves as a Flow-MER team to working in partnership to meaningfully engage with traditional owners to ensure a sustainable and equitable management of water going into the future. My co-lead, who I have mentioned already, is Emily Barber. Emily's online here today. She's from CSIRO. I lead the research component of Flow-MER, and Emily leads the evaluation component. Of course, a project of this size and scale is a partnership of many, and we rely heavily on the hard work, dedication and intelligence of our colleagues across a wide range of organisations. And particularly for the Flow-MER webinars, I'd like to recognise the Australian River Restoration Centre, Siobhan and Pat, who help us organise these events each week. The Flow-MER program, if you haven't heard about it before, is the monitoring, evaluation and research program led out of the Commonwealth Environmental Water Office. It is based around 7 selected areas, which are shown on the map there, and a basin scale integration program, which is the component that Emily and I co-lead. I would love to give you more details on this program, but to be perfectly honest, the Flow-MER website does a much better job of that than I possibly could. So please go to the website and you'll find wonderful and frequently updated stories about Flow-MER and what Flow-MER does. The research component is been going for a while now and draws heavily on what was the UCA program, which finished in 2019. The evaluation component arises from the LTIM program, which many of you will have heard of. That only commenced in the middle of last year. So we're just entering into our first combined research and evaluation reporting program right now. If you're interested in more detail about how all that works, and indeed if you want some detail on who are the key contact people for various components of the project, then you can find that via the Flow-MER Basin Scale Evaluation and Research Plan, which is available through the Commonwealth Environmental Water Office website. So have a look for that if you want to see more details, or certainly Emily and I would be happy to speak to you about any of the components of the project. The Flow-MER webinar program, this is the second series of webinars that we have run, and the original intent here was to actually just facilitate sharing of knowledge between researchers, local water managers, across research teams in the select areas in the basin, and between agencies. Much more so in this round, so in the second series of the Flow-MER webinar program, we are trying to much more explicitly enable and support adaptive management. And so because of that, we have each week we have not only the researchers presenting, but also we have a representative of the water managers and water planners presenting as well. And that's just to make sure that we are kept on task with respect to making sure that what we're talking about is relevant to policy management and planning of water use. So that's such an introduction today. I'm now going to pass over to our team for today. And so we have 3 speakers who are tag teaming it through today. Ashley McQueen from Deakin University is going to lead off. Then we will also be hearing from Daniel Stratford, who is with CSIRO, and Bruce Campbell from the Commonwealth Environmental Water Office. So I will hand over now to Ashley and let him get started.
So just as we're handing over to Ashley, a reminder for people to use the chat function. It's a good idea to have that box open and pop in any questions that you might have or comments, and we'll be sure to come back to them at the end of the session.
All right, so Ash is just going to share his screen. We can see it, Ash. We'll make sure we can hear you.
Winning.
There we go. We can see and hear you.
Lovely.
Thank you, Ash.
Thanks, Ross. So I'm leading off with a little piece of work that Shrine asked me to do, I guess setting a context for modeling. I guess if you think about it, modeling is all about giving us an extra tool to understand the world around us. So we start with the black box. Here, I'm showing the real world as an ibis. And this ibis here represents the ecosystem of the Murray-Darling Basin. This is the real world that we're interested in here. And over the top of that, there's a blue filter. This is the veil of unknowing. We can't see the basin at all places, at all times. We can't fully understand it all in one go. However, we can get glimpses of it. Through monitoring, we can look at the basin in a systematic way. That's in specific places and times. So this becomes the observed world. So as I'm illustrating here, they basically gave us little windows into the real world. And you can see those little windows are a little bit blurrier. Our methods are imperfect. And we don't get to see the full picture. And I guess that's the power of modeling. Through analysis of this data and modeling, it can allow us to join the dots, if you like, between the information that we do have. Now, it's worth noting that red outline that I've drawn, one, it's a vast simplification of the real world, the ibis representing the basin. And also, this is like my third attempt at drawing that ibis. Originally, it looked pretty wacky. And that is also reflected in the modeling process, that as we get more information and we improve our models, they improve over time. It's also worth noting, I think, that the principle of parsimony, that the model only needs to be as complex as it needs to be to meet the goals that we require. But that's not the end. The purpose of modeling is to have input into action. So to close the loop, the decisions and actions made by managers, which are informed by modeling, can have an impact, direct impact on the real world. And here, just illustrating that by perhaps an increase of the number of straw-necked ibis. Whether you want it, if it was a different ibis, you'd want that increase. It's a different matter, I guess. So now taking that setup, the idea of the different worlds, and putting it in a Flow-MER modeling context, we have the ecology of the basin. We have drivers, and we have the different themes represented here. So, for instance, vegetation and fish and so forth. And we know that there are drivers in the real world, focusing on abiotic ones. The hydrology, of course, is very key, and also represented here with a green box is environmental flows. There are a raft of other drivers as well, so meteorology and so forth. Through monitoring, we move to the observed world, where we have information about the ecology, we have information about the drivers. Through analysis of those relationships, we can draw out quantitative relationships or thresholds. And moving into this modeled world, we can apply those thresholds and relationships, or ecology flow relationships, combine those with the drivers to give us outcomes. And through a process of integration across the different themes and across space, we can provide outputs or information products to managers. And it's worth emphasizing that the process of going from vast amounts of data to a product which is tractable and useful is actually a significant step. That information can then be used by managers to have that impact in the real world. And just noting that there are also a bunch of other drivers, including social drivers, which drive the priorities of those management actions. So that's my little bit about, I guess, an overview of modelling in a more general sense. And now I'll pass back to Daniel, who'll talk about the aims of the modelling program.
Okay, so what I'm going to provide just very quickly is a high-level overview of the types of goals that we're trying to achieve in the modelling cross-cutting theme in Flow-MER. So within that theme, there's two different research activities. So the first research activity is the flow ecology responses research activity. So this looks at understanding the flow ecology of the different themes that we're looking to incorporate. And build these as hypotheses into a framework to test, understand the counterfactual. The second research project is the Deakin project. So this is more future thinking in terms of how can we use a broader range of data sets and bring these into a framework in an integrated way to try to unpack more of the questions beyond flow hydrology itself as well. So in terms of the high level goals that we're trying to achieve in the cross-cutting activity, so the first one is understand the flow ecology relationships as drivers or limiters of success. So creating that link between aspects of the hydrograph or hydrology or inundation and the environmental outcomes that we're seeing or trying to predict. The second thing that we're trying to achieve is to enable integration of themes into a common framework. So this is really important in terms of bringing things together in a way that we can look at outcomes across individual themes and have that more holistic view in terms of what we're trying to achieve as outcomes as well. The third one is really important, and that's understand the relative benefits associated with the Commonwealth Environmental Water, and I'll certainly talk about that a little bit more. Extrapolate to unmonitored areas, and this is one of the key benefits of modelling itself, is that we're able to build upon that general understanding that's developed through monitoring, create a framework that we can use to predict and understand outcomes beyond the monitoring itself. And of course, what we're trying to achieve is to contribute to basin scale and basin-wide understanding of outcomes. So again, this goes beyond the selected area resolution of understanding outcomes. So what I'm going to talk about is the research work which is happening in the flow ecology responses research activity. So the team for this is myself, Ashmita Sengupta, Luke Lloyd-Jones from Data 61. So just to come back to it, the key goal of what we're trying to achieve is the ability to predict the counterfactual. So what we have here is a hydrograph. The blue line represents the observed flow. So this is the flows that are passing through the gauge network. The red line represents what we're referring to as the counterfactual flows. So these are the flows that are observed flows minus the Commonwealth Environmental Water contribution. So the difference between those equates to the Commonwealth Environmental Water that was delivered to that gauge. So the difficult part of that is trying to understand what the relative environmental benefits of those two different hydrographs actually means. So this is where modelling comes in, and put very simplistically, the modelling sits within that little blue arrow up the top there. So it provides the link between the observed and the counterfactual hydrology and our ability to predict the counterfactual ecology. So if the observed flows produce an environmental benefit equivalent to what is observed, what we're really trying to unpack is what's the difference between those two hydrographs. So what we're trying to do is understand the types of relationships associated with ecology and the outcomes that are achieved, and then essentially model that for those two hydrographs. In terms of the flow ecology response modelling activity, so these are the range of sub-activities that we're undertaking to be able to achieve this. So the first part of that is our describing hydrology. So the hydrometrics and creating that meaningful representation of the hydrograph. Secondly, it's understanding the flow needs and responses of the ecology. And I'll go into more details on these. Thirdly, modelling responses to flow. And then finally, understanding what is where within the basin and providing our ability to extrapolate relationships and indeed where things occur as well. So firstly, that representation of hydrology. So the hydrograph itself is obviously very complex through space and time. So in terms of how we summarize that hydrograph to create meaningful links to both the types of management events that are occurring, as well as those how we link those events to the environmental outcomes that might be observed as well. So we had a talk a couple of weeks ago by Chris and Eric with regards to functional flows. And I think that that's a really powerful way in terms of creating meaningful links to functional ecology as well. So we can create links between the different theme indicators and different parts of the hydrograph and the hydrology in terms of what we expect. So peak flows, for example, will create a different response or have different will require different dependencies in terms of the theme outcomes as well, compared to base season flows. So fish spawning, for example, or vegetation inundation might require a certain flow threshold to do that. Dry season base flows might be important for, resilience or, adult survival during that period of stress, for example. So we're trying to achieve meaningful links. Secondly is relevant to management actions and the gauge flows as well. So not all gauges are the same, not all flows are the same. So here, the top hydrograph here, you can see it's very peaky and dippy. There's a lot of variability within the hydrograph itself. And indeed, where the Commonwealth Environmental Water is delivered is different in terms of where it occurs in that hydrograph as well. So you can see here that it's often being delivered to create peaks within that hydrograph, as compared to the second one here, where a lot of the Commonwealth Environmental Water is delivered to provide base flows. So having a method that's relevant to those different types of flow regimes across gauges, but also relevant to the types of management actions that might be occurring as well. And that changes through space and time. So here's the resource availability scenario. So you can understand that obviously in times of dry conditions, the types of management actions are going to be different to those that occur in wet periods. And the third quality that we're looking for in that representation of hydrology is the ability to generalize outcomes as well. So here you can see a cross-section of a riverbank and these sort of standardized flow components that very well align with the CEWO way of thinking in terms of low flows, bankful flows, over bank flows, for example, as a way of being able to generalize the hydrograph across different locations within the basin. So secondly is the flow ecology relationships as well, and this is obviously crucial importance to what we're trying to achieve. So this first figure here is a conceptual model of river red gum condition from Todd Wallace et al. And essentially what you can see here is different tree canopy indexes. So 14 is obviously very good condition for that standard vegetation. 0 is obviously not so well. What happens is obviously that when you have increases in flood frequency, you push the condition towards the better end of the spectrum there. So the more flows that you're having delivered to the needs of that vegetation stand, the better that vegetation stand is likely to be. And the inverse, obviously, going the other way, when you're not having those flows, you get a decline in condition associated with that vegetation stand. Another way of viewing that would be to look at the specific events and how they occur through time series within the hydrograph itself. So here the blue boxes might represent a breeding or a recruitment event where those flow requirements were met for the specific indicator. So you can see here that in 2015 water year, 2016, 2017, and then again 2019 water year, you had those water conditions being met. The blue boxes represents the flow conditions suitable for recruitment. So what you're seeing here is those temporal aspects of the flow regime and how that relates to the ecology of the theme indicators itself. So where the flow conditions are being met, you have an improvement in condition through time over consecutive years of those conditions being met. Part of what we're doing in the research activity is to look at multiple lines of evidence in terms of understanding where those flow ecology relationships actually occur in terms of, understanding the flow components, understanding the response relationships for our indicators as well. So the table on the left-hand side here, what you see is some preliminary results for non-woody vegetation. So this is work being done by Luke Lloyd-Jones. So you can see the types of relationships in terms of the R-squared values there that we're getting from our statistical models. The models themselves can be used in the predictive sense. So here you see the predicted percent cover versus observed percent cover using, the various covariates in terms of being able to predict those outcomes. What else we're able to achieve by that is to understand the different flow components from the hydrograph that are statistically significant for achieving the different outcomes as well. So we can use this to identify, priority areas in the hydrograph that might be important for us to consider in terms of those management outcomes, and also in terms of, additional modelling. So understanding what the drivers are that achieve our outcomes. So this is an overview of our dynamic state and transition modelling. So this is a mechanistic-based modelling platform. So essentially, it looks at the different theme indicators. The first step is to define the indicators and the type of metrics that we'll be using. So, for vegetation, it might be percentage ground cover, for example, or it might be canopy index. For fish, it might be, spawning events, or population sort of aspects. So once we've defined those different categories, it's the next step is to identify the important flow or inundation predictors associated with driving those, and the types of responses that occur in terms of the sequence of events required to do it. So that looks at the antecedent conditions, not just in terms of the hydrograph, but also in terms of the ecological state of the asset itself. So, things might be, take several years, there might be lags in terms of response times, for example. The final aspect of our work is extrapolation as well. So, and I'll talk to that shortly, but essentially what we're trying to achieve is that basin scale view in terms of what's happening with regards to outcomes for environmental water. And the approach we're taking for that is looking at A and AE essentially as a building block for extrapolation by understanding the habitat associations of the theme indicators itself. So within each A and AE type, or inversely for each theme indicator, be it a vegetation community or a fish species, we can relate that back in terms of its habitat use of an A and AE type, and also look at where there might be, as a hypothesis, where there might be different flow needs or responses within those different building blocks, those A and AE types, and then we can explore that with relation to the gauge flows across the basin itself. So in terms of this body of work, what does this provide? So what are the benefits of the work? So the first one is the ability to extrapolate hypotheses about how species and habitats respond to flow regimes. Secondly, ability to value the environmental benefits of Commonwealth environmental water at basin scale. So unpacking what the difference between the observed and the counterfactual flows are in that modelling sense. Thirdly, ability to explore scenarios and seek solutions to basin scale watering decisions. So looking at trade-offs, for example, in terms of where environmental water can best be put to use at that broader scale. Ability to assess outcomes and trade-offs in a repeatable and consistent framework as well. Provide a framework for adaptive management and adaptive modelling as well. So learning by doing. So it's not just about improving our management practices, but also about our modelling practices as well. So, you know, our response relationships are hypotheses for how the system operates. So as we learn more information, update those response relationships or our understanding of the water requirements to, you know, improve our modelling capacity as well. And with that, I'll hand over to Ashley.
Right, we can see you, Ash.
Can you hear me?
We can
Ross?
hear you as well. All is good with the world.
Marvelous. Thanks, Daniel. I'm going to talk about the integrative modelling project. I'll start with some, I guess, the overall aims, what our plans and intentions were for the project, the progress we've made, how the frame operates, and finish with some prospective uses of the model. So I guess the overall aim is to create a modelling framework for evaluating the effects of environmental water at the basin scale. And key elements of that are the ability to integrate across themes, to draw information from the themes. And you'll see how that works in practice as we go along. But also to be able to say something about parts of the basin where we don't have monitoring data for. We want to make use of this amazing trove of data and translate it into scales and forms of information which are useful to managers. To begin with, we are going to be looking at creating a framework which will be progressed in future iterations of Flow-MER. And by, I guess, this efficient use of detail, it gives us the potential to run scenarios which might go for a decade or so. But to begin with, we'll be looking into the past, hindcasting, looking at the impact of environmental water in past years in different areas of the basin. I want to note that in this way, it's not a replacement for local models or species-specific models, which might give you specific predictions about the number of individuals or success like that. But it can draw on relationships identified by those models. And likewise, the model is not going to seek to tell a local water manager what they should be doing, just providing a tool which can add further information for them to use. Right, stepping now into, I guess, the overall plan for the integrative modelling. We starting with ecological responses, which are provided us by our partners in the themes, and combining those with a set of drivers. Again, the identity of those is drawing on discussions with theme colleagues to provide outcomes for species of interest in different locations of the basin. Looking for integrative variables which allow us to integrate information across different themes, and also keeping an eye out, if you like, for if there are any variables, perhaps heterogeneity, which provide a powerful summary of those. And using that, giving integrated outcomes for the basin. Also noting that there's the possibility of using the data that we have to validate some of to compare to the outcomes that we find. And noting also the importance of and considering uncertainty. And I'll come back to some of these points later on. I first want to run through a few research questions because there's a lot of research actually involved in putting this framework together. So how do we best define ecological responses? What's the best set of scale variables? We want it to be as parsimonious as possible. That is only using the amount of data or variables that suit our purpose. What variables can best integrate across taxa? How can we extrapolate in scale and space and time? Very important question. Again, also have questions about uncertainty, capturing and expressing it, and matching other data, and ultimately working towards providing a tool which gives us the ability to do scenario comparisons for evaluation and management. So zooming in a little bit on the bit of work that we've been beavering away at. To begin, we have this collecting a set of potential data sets and merging that into a common format, combining that with ecological responses using a life cycle approach and the concept of strictures and promoters, which I'll explain in a moment, which will give us these outcomes. Again, and then we'll come to scaling and integrating. So the basic building block of our model, our framework rather, is the A&E classifications, which are effectively kind of vegetation types. And we have polygons for those throughout the basin. We have been focusing for testing purposes on the Lachlan, and for visualization purposes, sometimes we just use this little snippet of Cumbung Swamp. So building blocks are those A&E polygons. We then combine that with a number of different data sets. Here, this is a soil moisture raster data set. You can also overlay polygon data sets, such as climate types, for instance. And we can use an array of different, I guess, summary statistics or metrics to combine those to create maps like this. So maps of drivers in a form which makes sense according to the ecology. So for instance, we have like a 5-day minimum soil moisture and a 28-day maximum soil temperature. So it's an example of one of these underlying driver data sets. Now let's touch on the strictures and promoters concept. What you're seeing here is a life cycle for a black box. And the basic concept is that for a species which is to go from one life history stage to a second life history stage, there can be factors which can promote that transition or detract from that transition. So, and there can be quite a big range. I think Heather McGuinness did this diagram in particular. But yeah, the ones in dark blue are flow related, but there can be lots of other potential strictures, including grazing and salinity, some of which we can address through management actions. And that's the paper which it came from. So working with the vegetation theme, and Cherie in particular has been very helpful, and in the Lachlan, we've applied that concept to create a test plant, which is based on a non-woody plant. And for each of the transitions, we've pulled out some of the key strictures or promoters. So they're kind of like two sides of the same coin. So here you can see that for a seed to make it through to a seedling, the soil temperature can't exceed 60 degrees, and it requires inundation for 5 days. Equally, they require the growth period for the seedling to become mature of 6 weeks with a soil moisture of greater than 10%. We are also, in concert in our testing, modeling another species, again, based on a real life species, and so which inputs into the life cycle here. So for this species to be successful, it requires that the competitor was not successful in the previous year. And fruiting is dependent on germination and successful growth period. So what does that look like in space? Well, we can overlay that on our data, which is, we have daily data. So yeah, you can see that the bright yellow means that there's a large number of days, which is past that stricture, if you like. But let's say the yellow means is a high number of days. And here, when you stack a number of different strictures on top of each other, the number of days which are passing those tests drops. I'll note that, yeah, we've been working with soil moisture at the moment, but that the hydrology will be coming down the track very shortly. So integrating and scaling outcomes. So on the left panel here, you can see that these are the number of days passing stricture for each of the ANAE polygons where that plant type is expected to be found. And so we can have these for a whole range of plant taxa and eventually for other sorts of species as well, birds and fish and so forth. But then there's this process of scaling this up to the basin scale. And so on the right panel, what we've done there is the color here reflects the area of the Lachlan which has high numbers of day passing. So again, the yellow is a high number of days passings. So there are so many options about how to do that. So we're going to be talking with CEWO next week to see what are the forms of outputs which makes sense to them or are going to be useful to them. So that'll be one direction which is driving that work, that research. And I guess the other side, of course, is what makes ecological sense. And we can provide outputs which are at the theme level, could even be for a particular species. Bruce yesterday was saying that the black box is actually has a greater impact on, or more valuable in some respects to some other little form or something. Sure, you don't get too offended, but so we can provide outputs at that scale for the species across themes, or integrating across themes for a particular theme. So just going back to this diagram, so this is the bunch of work that we've done so far in a testing capacity. We are actively researching on these integrative variables and also working with CEWO to see what those outcomes are going to be like. We have created the potential, the capacity for characterizing and working with uncertainty and validation. That's available to be bolted on, I guess, to the framework as it stands. So continuing on, so this first chunk of work is really about setting up a framework and testing it and making it so that we can have input from the different themes and it's flexible, so we can have different data layers which are input according to what themes think are important and relevant. But looking forward, once the framework is more fully parameterized, it gives us a whole range of different uses at different scales. So you can use these integrative variables at the basin scale. You can look at a time series of these, perhaps hindcasting, to see how parts of the basin are tracking where we don't have monitoring data for, or have the potential to drill down into specific locations and look forwards and compare different scenarios in the future. Now, I believe that Bruce might have something to say about some of these matters at this point. Are you there, Bruce?
I am indeed, Ash. Thanks very much. And hello, everyone. There's some people on this call, some names that that take me quite a way back to some modelling tasks that I, in fact, project managed around about 20 or so years ago. Terry Corn, Jane Roberts, I did see your names pop up. Hopefully you're still there. A reflection, I guess, on the journey that modelling's taken over that time. Once upon a time, flow ecology relationships was something that we relied on experts, such as Jane, to, I guess, provide that interpretation of hydrologic models. So when I think of models, I'm usually thinking about hydrologic models and in terms of them being black boxes. And I don't mean the trees. I guess on reflection and talking to Ash and Daniel and Joanne about this particular presentation, I've had a bit of a realisation that models are much more than just that. And that's not to denigrate those black boxes. In fact, they're extremely important and can inform very, very complex management decisions that couldn't be made without them. So I guess what I've just reflecting on here is three things. So Ash, if you're able to, you're still sharing your screen, if you could just, we did skip one slide of yours. I want to come back to that. But the three things are that conceptual models, and conceptual models, I think, is where, this is an overused term, but some of the best available science is actually contained in the conceptualisation of these flow ecology relationships. And this is something that we found through the review of LTIM and UCA, is that there's merit in actually revisiting some of these, checking in that we're looking at the ones that are of, I guess, the greatest management relevance. As you mentioned about black box, I'm not sure I mentioned a FORB yesterday. I'm not sure I know much about FORBs, and I probably know very little about black box, but there are some indicator species that drive environmental watering requirements more so than others. So that's, I guess, the key point, is that we need to make sure we're looking at the right ones. And when we need to make sure that we're testing and refining those relationships, because with a limited portfolio, managers have to make trade-off decisions, you know, we need to ensure that these things are made using the best available information. So the known in the Rumsfeldian sense is basin scale evaluation. We have a need to, I guess, upscale, and LTIM and now MER have been designed with that in mind, that we are only able to monitor a relatively small number of areas in with high intensity, but we're required to report and to adaptively manage outcomes across a much broader area, including those places where we are delivering environmental water in the absence of having some of that detailed monitoring effort. So yeah, we need to learn what we can from where we're doing it, and lucky enough to be in a position to monitor it intensively, such that we can then have greater confidence that we're getting things right in other areas. I think that what you guys have been describing, and this goes to Daniel's point about understanding. It was the last point on his modelling goals slide, that long-term planning and the work that you're doing has the potential to inform some of the more strategic decisions that are necessary at times, and this goes beyond CEWO. It goes to NWA's decisions about basin plan settings. It goes to the state's testing of long-term watering plans, and they already do have some of that capacity and knowledge, but the work that you're doing can contribute to building that. So yeah, there's also a need in a long-term planning sense, and the work that you're doing is potentially very useful for that. I guess there's one more epiphany I had, and that came from both Ash, your principle of parsimony, and Daniel's comments around that too, if I could have a go at merging them together. You said about the principle of parsimony that the model only needs to be as complex as management needs. And I typed a little comment there in the chat field about that. Our management needs are very, very complex. The challenge is in presenting this information in a way that managers can use, given we don't have the benefit of your background and training. But Daniel said this, and I'll paraphrase it by saying, the manager is part of the modelling process. So I think when we're thinking about these models, we also need to be realising that the interpretation is absolutely a fundamental part, and you both described feedback loops. And so, yes, I think that's a really, a really useful reflection, is that it doesn't really matter how simple or complex the model is. It's only as good as the interpretation of it. And that then leads to a feedback loop that can be used to improve that particular model. So they were my perspectives. So yes, excellent, the three
Bruce.
needs.
Thank you, Bruce. That's really terrific.